Endurant. Welcome, ladies and gentlemen, dear colleagues. And my name is Stacey Nestler. Jakob has said it. I have been working as a material scientist for a long time. Now I am also working in the field of CMC, ceramic matrix composites, at the professorship of lightweight structures and plastics processing at the Chemnitz University of Technologies. The webinar should help to better understand the composite material group, ceramic matrix composites. This innovative group of materials will be explained in more detail in the presentation and classified into the system of materials. The differences between ceramic monolithic materials and fiber reinforced ceramics are elaborated, and the webinar range from a brief historical insight to today's innovative manufacturing methods and applications. In addition, current research at Chemnitz University of Technologies will be presented too. So, yes. The next slide, okay. This is the outline for today's lecture. I will give you a short historical insight into ceramic matrix composites, so-called CMCs, say something about non-oxide and oxide ceramic matrix composites, about the technologies, about the application cases, and then give you a short summary. Because the field of CMCs is very broad, I can only give you a small overview, like a view through a keyhole. This overview shows you a structured classification of materials and material systems. In the upper line, you will find the main groups of monolithic materials, polymers, metals, ceramics, and natural products. If these materials are combined with reinforcing components, such as fibers or particles or other materials, like carbon nanotubes, platelets, viscose, and so on, then you get the so-called composite materials. Composite materials are divided in the polymer matrix, metal matrix, ceramic matrix, and interpenetrating fast composites. This means, you see this in the right-hand side, they are macroscopically homogeneous and consist of at least two components. If I combine all these materials presented here, I come to so-called material compounds, but that is another lecture, and this overview must suffice for now. What you can see well now, however, is if you combine the ceramic matrices with the reinforcement components like fibers, then I come to the ceramic matrix composites. So the development of materials is the most important driving force behind human progress. Therefore, the Eurocentric periods were named after the associated materials such as Stone Age, Iron Age, Bronze Age, and so on. Diverse property profiles today, you see this at the end, on the right-hand side, require complex material systems so that they can meet the requirements. Some keywords for today are drivers of this development, such as energy efficiency, resource conservation, climate protection, and so on. Already in early history, composite materials such as clay ceramics were produced without knowing the scientific context. If we now make a big leap into the modern times, you can see the ceramics composites in dark green, can you see this here, as the youngest group of materials. And the development of CMCs is closely linked with the fiber development. In 1964, Cook and Gordon developed a concept to increase toughness by modification of crack propagation in the composite by introducing reinforcing material. And this is not a picture of me in the left-hand side. This is the Venus of Dani Wester-Nitsche. She is 27,000 years old, and it's one of the oldest ceramic products and consists of a mixture of animal, bone, meal, and clay. And on the right-hand side, you see the brick maker on the one of the more manual occupations in ancient Egypt to make bricks. Nile mud was mixed with sand, straw, and water, slapped into wood molds, and slapped out onto the ground to dry in the sun. Well, you can see that in practice, the effects of reinforcing components were known, but the science took a very long time to implement this in technology. So the application fields of the ceramic materials are very diverse, of course. I don't want to report now on which applications are available in the monolithic materials in the following slides. However, I want to present the differences between the monolithic ceramic materials and the fiber reinforced ceramic materials. So here you can see the advantages of the monolithic ceramics. I think you notice that we have there a very great temperature resistance, low density, high compressive strength, high Young modulus, and so on. Very interesting also the great corrosion resistance and the good wear resistance. But there are also some drawbacks. The brittleness, the fracture toughness, low tensile strength, and also the low temperature shock resistance. So we have there some drawbacks, and we want to solve this with the ceramic matrix composites. And you see here what are the differences if I compare this with the monolithic ceramics. We have there a high temperature and thermal shock resistance. These materials are quasi-ductile, fracture resistance, and capable of impact loads. We have a high damage tolerance and so a long lifetime. And you see this here on the right-hand side. If you plot the specific strengths against the temperature on the left-hand side, you can see that the fiber reinforced ceramics have the best strength by weight in high temperature applications. Today, the heavy nickel alloys or nickel-based alloys in particular are used for high temperature applications. Ceramic composites are also interesting because it is possible to use thin wall parts with a good strength at high temperatures, or even with strong temperature changes or shocks. I give you them some examples a little bit later. Here, yes, what is the reason for this? That we have increasing in the fracture toughness, in the damage tolerance, or preventing the brittle fracture. What is this? What is the reason for this goal or for these properties? This is the dissipation of crack propagation energy is the reason why CMCs are quasi-ductile. In the diagram, you can see the curve for this, and you see here this graph of a fiber reinforced ceramic. There's an energy dissipation of the cracks through the fiber reinforcement. And a little bit better, you can see this in this slide. There are 7 mechanisms that can explain the effect of fracture toughness in fiber ceramics. All mechanisms aim to increase the fracture energy of a material through corresponding structural optimization. Since the specific surface energy is conditioned by the crystal structure and the direction of the cleavage surface, an increase can hardly be achieved there. It therefore remains to increase the fracture surface itself by deflecting a crack from its plane path perpendicular to the tensile stress. Furthermore, one could bridge a crack with one or more particles, similar to joint boards with nails. Furthermore, one could plant the tensile stresses at the crack tip by superimposing or corresponding compressive stresses that must be generated in the microstructure. Most of these fracture energy consuming dissipating strategies can be realized by multi-phase microstructures in which a second ceramic or metallic phases interacts with the crack. This leads to so-called particle or fiber reinforced ceramics. It would be too extensive today to explain these mechanisms scientifically. That would be a separate webinar. I only want to give you some points for this, that we have here with this ceramic matrix composites a ductile material. In addition, the model, according to he and Hutchison, explained the crack deflection at an interface of two different materials with the help of fracture mechanics. As the figure shows, the boundary curve for the ratio of the specific interfacial energy and the surface energy of the fiber is plotted against the offset of the Young modulus of fiber and matrix. Below the boundary curve, at low interfacial bonding, crack deflection occurs at the fiber matrix interface, which leads to interfacial detachment or the bonding. Above the boundary curve, you see the interfacial bonding is too high and no crack deflection occurs. Thus, the crack completely penetrates the fiber and brittle fracture of the composite occurs. And so we come to two concepts. The one concept is the weak interface composites, where I decrease the interface bond. And the other model is the weak matrix composites, WMC. There I have weak matrix, decreasing of the matrix stiffness. What you see here in this picture, the WIC model and the WMC model. Often there's also a combination of these two concepts. For the most parts of the left-hand side, the WIC concept is for carbon fiber reinforced in a silicon carbide matrix or silicon carbide fiber in a silicon matrix, the so-called black ceramics. And the WIC concept is often with a coating of the fibers. And the so-called white ceramics on the right-hand side, these are the aluminum oxide fiber in the aluminum oxide matrix composites, or malite concept. They followed the WMC concept. And you see this in these pictures, which effects I have in these two models. Also here some SEM pictures. You see on the left-hand side the weak interface composite, and here you see the crack path in the interface of a 6-SiC composite. We say this in the community. This means I have a SiC silicium carbide fiber in a silicium carbide matrix. And on the right-hand side, you see there the weak matrix. This is a composite of an aluminum oxide fiber in a malite matrix. Yes, and you can see this very good, what I mean with these two models. The main differences between the oxide CMCs and the non-oxide CMCs are that the non-oxide CMCs have a better strength, better Young modulus, thermal conductivity, and higher melting point than the oxide CMCs. However, in case of OCMCs, the advantages are better insulating, better oxidation resistance, and a cheaper production process. Well, now from the theory to the technologies and the practical applications. Only a few processes are suitable and are established for an industrial production. Commonly utilized processes are based on impregnation of a fiber structure or of a textile preform. There are many manufacturing processes, but only a few have become industrially established. Here is an attempt of classifying the processes according to the aggregate state of the raw materials. In the following, I will only show you the most important technologies. In the technologies for the non-oxide fiber ceramics, means the black ceramics, The processes have become especially established, like chemical vapor infiltration, liquid silicon infiltration, liquid polymer infiltration, and pyrolysis, and the ceramic slurry infiltration. Today, I only want to talk about the LSI process, which you certainly know from the fiber ceramic brake disc, I think so. And there we have a lightweight structure with a good damage tolerance, a very good corrosion, and wear resistance. So the whole process is very complex and consists of 3 different steps. First, a carbon fiber reinforced plastic is produced by a hot pressing process. The production is realized in a number of manual production steps, which lead to high production costs and results which are difficult to reproduce. During the next step, the matrix polymer is transformed into a carbon matrix by means of pyrolysis. And however, during this process, a lot of cracks form within the matrix caused by the matrix shrinkage. The result is a porous CC composite. This means I have a carbon fiber in a carbon matrix. And the last step of the production process is the infiltration of the cracks with liquid silicon by capillary forces. The reaction of the liquid silicon with carbon forming then the silicon carbide takes place in the area close to the cracks, and the final product is then a heterogeneous CC6 composite. In this case, this means I have a carbon fiber in a carbon silicon carbide composite or a matrix. So, and now, well, some examples for non-oxide fiber ceramics. First, here from the Schunk company, you see some examples in the case of carbon fiber and carbon matrix CFRC composites, some radial fan, convection fans, charging frames in different forms, oven sport parts, or aid protection, fasteners, heating elements, or other heating systems. You see here we need ductility and with thermoshock, with high temperature use cases. Also, another example is this. Another example is in nuclear fuel cladding and reactor core structures could make reactors worldwide safer. You know this disaster in Fukushima and the nuclear power plant's loss of cooling led to combustion of zircon alloy cladding, subsequent explosion and radiation release. If CMC cladding had been used instead, the fuel rods probably would have lasted until cooling was restored. Or here, some engines, turbine components, advanced materials take fly in the LEAP engine featuring ceramic matrix composites developed over a quarter century by GE. Brake discs are well known in high power cars, in luxury and sports cars classes. Compared to cast iron discs, they have a weight advantage up to 40 kilograms, little wear, no fine dust, and 4 times longer service life, but they are too expensive. Brembo SGL is the world leading producer of carbon ceramic brake disc, and the product portfolio currently includes 3 types of with many models of carbon ceramic discs. Black ceramic composites are used also as thermal protective structure in space travel. Here are some examples as nose cubs or space gliders. Further possible applications as heat exchanger couplings, plane bearings, gears, exhaust gas turbocharger, pistons, also in ballistic applications, or also in medicine as implants. The ceramic slurry infiltration is often used for OCMCs, O for oxide CMCs. The textile preform is infiltrated with the slurry consisting of powder and binder. This is followed by draping or laminating, drying of the green botting and the binding. This is followed by a sintering process. And there are many variations in the process according to the components and also in the preform technology. Some examples here from Walter Pritzko. He is also here in the auditorium. He knows the oxide ceramics better than I, and he is from the ceramic bleach company. Thanks for these pictures. You see some burner nozzles for oil fired burners, or on the right hand side a small burning chamber. So the lifetime factors was increased, or respectively OCMCs is a material where the metal material doesn't work. Or here some burner lenses in the use of metals. There is a destruction after short time, and with OCMCs there is not any changes in the area of the outlet holes. You see this a little better also here. OCMCs does not accumulate carbon, firing holes very clear and unchanged. Other examples are the carriers for heat treatment processes with small thickness, with great dimensions. You see this here some examples up to 1 meter by 3 meters is possible. And here carriage working at extreme thermoshock cycles. This is an important other thing compared to the monolithic ceramics, from room temperature up to 1040 degrees. Components for microgas turbines, combustion chambers. Here you see also the dimension of this chamber, and burner nozzles for the microgas turbine capstone C65. Other example here, components for volumetric ceramic receiver for concentrated solar power plants, a solar absorber with a spectacular height of 2 meters, of 2.5 meters. And you see here a picture of this prototype from the ceramic bleach company. Here, Walter Pritzko showed a lightweight structure for unmanned aerial vehicle with thin-wall structure, and here want to show that the CMCs can fly with a thin-wall structure very good. Now a couple of examples from Mr. Kunze from the Whitebox company. Some production tools, various charging baskets for heat treatment of metallic components at temperature up to 1200 degrees. There is not a shrinkage and a very long life, and also a hybrid tool with mesh basket of OCMCs with an insert, you see this, of a CFC, of a carbon, of a black ceramic frame as a carbon diffusion barrier work there, the OCMCs. Here, a heavy duty charging rack for high temperature processes, or some other charging devices and goods carrier, grid plates or grid trays produced with the Whitebox wrapping process. This is also very interesting that they use as a textile process the wrapping process. Now a couple of examples from Mr. Hermann in Ceram in Germany. Here are some ceramic louvres, hot gas flap for application temperatures also up to 1250 degrees as a modular construction with a variety axis modulus. Or here, thin-wall ceramic shielding spiral for inductively heated workspaces, or heat shields for a re-entry into the atmosphere when I come from Earth or from Mars in the future. Here, a roller oven with gates, also in modular design. And here's interesting that the modular construction compensates the thermal expansion and the stresses with their move-over segments with overlaps and slotted holes. Here is an example from Dr. Thomas Wanzer from the Schunk Kunststofftechnik GmbH. And here is a hybrid charge carrier. This is used today. The name from the Schunk company is Dura Fox. But what is the structure? We have the substructure for creep resistance of CC. This means you have a black ceramic with carbon fiber in carbon matrix or graphite, and then thin-walled OCMCs. They support to prevent decarburization of metallic charging material. And no flaking in case of thermal shock is there. Short process times due to low dead white. Also can the process charged with a robot. We have there also a modular design. This is good for repairing, or we have there a simple conversion, and the lifetime is very longer compared to a steel. At the beginning, I showed you the slide, you remember? The weak points are already incorporated now, and this is here the case. We have by the CMC high production cost maybe, and these are also manual processes often. These are niche products in the high price segment, almost medium industrial applications. And so the following tasks arise, which we will address. These are expansion of the market by publicizing the outstanding performance of the CMCs, or development of cost-efficient and reproducible manufacturing processes, or the realization of complex geometry via injection molding, 3D printing, or profiles with extrusion or pultrusion, because these are mass production technologies, and so I can decrease the costs. And also can we use the textile for load-bearing design. And these are our tasks here at the Chemnitz University in my research group. You see this here in this table. We work in the injection molding processes for near-net shape productions. We try produce the products with inliners for a load-compatible design. And also we can use our tools for two-component injection molding. And the newest is that we use the additive manufacturing process, pultrusion and extrusion, and the same is also by the oxide ceramics, because our goal is to decrease their costs. So here are some examples. We are transferring the SIM process, means the ceramic injection molding process, which has become established for the production of monolithic ceramics, to the production of OCMCs. So we have to adapt the raw material system and also the process parameter. This is not so easy. This is a time of research to come to the best feedstocks. And the compounding process can be used to add some additives that can functionalize our products and also leads to a change to a denser matrix. You remember I have told you about the WMC model and the IC model. And by the OCMCs, we have often a weak matrix, but with the injection molding, we come to a higher density of the matrix. And in this European project, OCMC is functionalized with CNTs to create electrical conductivity for a sensor function with the professorship of Professor Kanun. And the second technology to be developed is extrusion printing for the production of complex components. You see this on the left-hand side in orange, and with the feeding of a continuous fiber, because our ductility depends on the length of the fibers. Here are some SEM pictures showing the orientation of the fibers during the injection molding in the middle, the fracture toughness over the binding on the fibers from the matrix and the matrix crack path, and below the formation of a CNT network. You can see this here very, very good, what I mean with the effects or the effects of ductility in the CMCs. Here are some pictures of our first printed parts with a new feedstock, short fiber reinforced, also already with ribbing on the right hand side below. You see this, and now we are trying our hand at continuous fiber reinforcement with our extrusion tool, which is feasible with our printer, I have said. And here the insertion of the CNTs was successful, and higher conductivity was demonstrated with increasing the CNT content. You see this on the right hand side, and also in the middle our CM image where you can see the network of these CNTs. For the non-oxide CMCs, we have also implemented the injection molding, which offers both higher reusability and a higher degree of safety due to the mass technology with a closed tooling. We use their phenolic resin, and there is better to use a closed tool. We were able to achieve progress in protrusion, also of profiles. And if you see here, the compounding process has been redesigned to achieve longer fibers for fracture toughness. And in the microstructure picture, you can see the degree of siliconization achieved, which makes us very optimistic for the future. Energy dissipation effects, I have told about this. You see this here in this picture very good. I have a crack deflection, a fiber fracture by injection molding, fiber fracture, and then also the matrix fracture. You see this. So we have a pull-out effect also, and you see this on the right-hand side, the pull-out effect. You can see there. Also, the fiber alignment was demonstrated, which is created by injection molding. You have there an alignment of the fiber in the direction of the flow by the injection molding process. And so we can also this use for a load-oriented design. It was also possible to produce at first CFC profiles via protrusion with smooth surface quality, no delaminations, a good dimensional stability, and this by a fiber content of 67%. And the ceramization is in progress now today. So now I give you a small summary. The CMCs, as the youngest group of composites, has great market relevance in the well-known high price segments, but also, and this is important, in the average market. We have to solve some challenges, such as opening up new markets and new application by publicizing the innovative material. Realize the substitution of heavy metal alloys by CMC with a better property portfolio at lower density. So we can say this is a game changer potential of lightweight constructions. And the dissemination of know-how on the material to arouse interest in its application. Also, the development of resource-saving technologies that make the material more efficient and cost-effective with new technologies with required sustainability. This means repairability, recyclability also. Or sustainability with a good economy, ecology and social aspects. Circular economy and the digitalized processes, so-called KI, as peripheral conditions for a successful implementation of the lightweight strategy. And it's very important today in this time that the stakeholder cooperation for faster implementation of the object is necessary. So I thank you very much for your attention, and I would like to thank the colleagues and the partners which made this presentation possible and contributed to it. My thanks to Walter Pritzko, to Albrecht Herrmann, to Matthias Kunz, and also to Thomas Wamson. Thank you so much.